Today, right now, inside the world's top tech companies, artificial intelligence generates over 75% of all new code. But this massive surge in raw output hasn't created a utopia of perfect software. Engineering teams are currently shipping more bugs, triggering more production incidents, and accumulating more technical debt than they did 2 years ago. This chart illustrates a dynamic known as code overload. While the sheer volume of AI-generated syntax skyrockets, the area representing technical debt and system failures is rising exponentially right alongside it. When unmanaged, high-velocity AI agents output syntax without strict boundaries, you get severe code churn. Code is written in seconds, found to be flawed, quickly revised, and ultimately deleted. Prompts that describe a general idea, often called vibe coding, allow non-engineers to build functional prototypes. But assembling a quick prototype by describing what you want is entirely different from the rigorous discipline of professional AI-native engineering. The bottleneck in software development is no longer the physical act of writing syntax. The cost of generating a line of code has effectively dropped to zero. Because code generation is cheap now, premium value lies in system architecture, in deep product sense, and critical verification of machine output. To understand how this shifts the economic value of developers, we can look at this matrix from the BCG labor disruption model. The y-axis tracks task automation potential. Routine coding tasks, like generating boilerplate or basic crowd operations, score exceptionally high here, pushing software engineering well into the danger zone for automation. But the x-axis tracks the counterforce, demand expandability. This measures the business appetite for new digital products, continuous optimization, and feature expansion, which is practically infinite. When you drastically reduce the cost and time required to build software, organizations don't stop building. They use those efficiency gains to scale total output. This dynamic pushes software engineering firmly into the top right quadrant. It is an amplified role. Compare this to a basic call center representative. The demand for resolving customer complaints is bounded by the exact number of complaints. If an AI resolves them faster, the company simply requires fewer human reps. That role is substituted. While AI easily substitutes entry-level tasks of writing boilerplate syntax, it heavily amplifies a senior engineer's ability to design, test, and ship complete systems. The macroeconomic data is clear. Software engineering is not dying. It is evolving into a discipline of orchestration, where engineers command AI to meet a continuously expanding demand. Operating as an orchestrator requires moving past basic prompt engineering. This diagram shows the shift to context engineering. On the left, a standard text input points to a language model. On the right, a structured network of files feeds directly into an AI's working memory. The quality of AI-generated code matches its input specifications. An agent's output is bounded by the architectural logic you provide. Persistent context files, like a claude.md, containing your coding standards and linters, are no longer optional. They are core project infrastructure. A common developer mistake is trying to bypass this precision by dumping an entire unfiltered codebase into an agent's context window. This immediately leads to a condition known as context rot. As the token window expands with irrelevant noise, the agent starts forgetting rules. It loses focus, repeats previous mistakes, and begins generating hallucinated logic. The solution is to use atomic, highly targeted context blocks, provide precisely the files needed for a specific task, and deliberately reset your session for every new ticket. Tools like the Model Context Protocol, or MCP, serve as a universal standard to safely connect agents to these specific external data sources and tools. To maintain consistency across an organization, these shared context libraries must become the core currency of the engineering team. An orchestrator's primary coding language is no longer Python or JavaScript. It is the precise architecture of the context they build for their agents. The traditional linear software development lifecycle breaks down when exposed to autonomous AI. It is replaced by a parallel framework called the agentic development lifecycle, or ADLC. The first pillar of the ADLC is a mandatory planning phase. Before any syntax is generated, a planning agent must research the codebase, flag ambiguities, and propose a structural blueprint for human approval. Once approved, you transition to the building phase, commanding agent swarms. This requires rigorous problem decomposition. You break complex problems into discrete, AI-manageable chunks, which parallel builder nodes implement simultaneously, without context pollution. In the testing phase, dedicated testing agents write failure plans first. All tests must fail at the beginning, incrementally passing as the builders execute the code. It is test-driven development reincarnated. You establish quality control by pitting these specialized agents against each other. A planning agent will challenge a builder that takes a shortcut, and a testing agent will flag a builder that skips coverage. Industry leaders like Mark Zuckerberg expect these agents to operate with the proficiency of mid-level engineers by the end of 2026. Within the ADLC, the human operates as the tech lead. While the agents handle 80% of the routine implementation, the orchestrator handles edge cases, custom logic, and the final verification. Mastering this parallel machine execution is what transforms a 10x engineer into a 100x orchestrator. But this speed carries severe risk. Research consistently shows that roughly 45% of AI-generated code currently contains security flaws or weaknesses. AI-native development is generating new attack surfaces significantly faster than traditional manual security review can address them. This includes entirely new threat vectors like slop squatting, where an agent reaches for a hallucinated software dependency and pulls poisoned code into a secure environment. When AI models hallucinate package names that don't actually exist, attackers register those exact names. The next time an agent asks for that dependency, it pulls malicious code directly into your supply chain. There is also the emerging enterprise threat of agentic authorization. Without strict boundaries, autonomous agents can bypass restrictions and pull from unauthorized databases at machine speeds that human oversight simply cannot track. Securing this workflow requires non-negotiable technical guardrails. This means OS-level infrastructure sandboxing, autonomous verification loops to catch vulnerabilities early, and mandatory human review for critical functions like authentication, payments, and PII handling. In the agentic era, testing raw AI output without isolated execution environments and hard verification is a guarantee of systemic failure. To execute this safely, an AI-native engineer's schedule looks drastically different: 40% context setting, 20% code generation, and 40% careful review and verification. Compare that to the traditional model, where code generation dominated the vast majority of a developer's time. Because the generation step is now nearly instantaneous, the time sink has completely inverted. Building context architecture and proving that the code actually works are your required areas of deep focus. Delegating the execution phase does present the real risk of skill atrophy for organizations that over-rely on machine output. To prevent this, engineers must occasionally work without AI. Preserving foundational problem-solving abilities ensures you can still function when your tools are unavailable or subtly wrong. An agent can generate a login page, but it cannot understand why users abandon a sign-up flow. AI cannot replace human product sense, empathy for the end user, or deep domain expertise. Instead, the technology amplifies your existing knowledge. Senior engineers achieve exponentially better results, precisely because their foundational judgment allows them to guide the AI more effectively. AI agents will not replace the systems-level developer. They will simply replace the developer who refuses to step up and lead the AI as an orchestrator.